everything that is written in the PowerPoint, you do not need to write down because it's there. But if there are things we talk about that aren't there, you might take notes on those things. Okay. How many of you have been to Statue of Liberty? How many of you have been up inside the Statue of Liberty? That means you went quite a while ago. Because
I think I went, but I was like 3.
after 911, they wouldn't let anybody up inside anymore. That's so unfortunate. I think they're afraid that somebody may smuggle a bomb in and place it in there and blow up the statue. I don't know. They just don't let you up in there anymore. But when I was it was the summer between my 8th and 9th grade year, our family went, and we lost our sister on Liberty Island. There were people all over the place. So, this was a long, long time ago. It was summer of 1970, actually. So when my oldest son graduated and we hadn't taken any great big vacations, we just decided to go back to see. So what we did is we went down to Walmart and we bought 4 different T-shirts, a set. There's 9. We have 9 kids, so we bought 11 T-shirts that were bright yellow, 11 that were red, 11 that were white, and 11 that were navy blue. And every day we'd get up and we'd put on the same T-shirt. It was so easy to keep track of people. You should have. My wife and I, we were Mount Rushmore on this trip, and my wife and I were tailing. We were going down to watch a video about how they made it, and the kids were all excited, and they went running ahead of us, all 9 of them. And we rounded the corner just as this husband said to his wife, "It's the attack of the blue shirts." And he looked up, and there we were, like, it's theirs. Anyway, we had fun on the trip. We were in Washington, D.C. for the 4th of July, and that day we didn't all put on the same color. A third of us put on red, a third white, and a third blue, and we went and watched the fireworks on the mall. Anyway. How long is the Statue of Liberty's arms? Her nose is 4 feet 6 inches. Say that question real loud.
How many noses fit in her arm?
How many of her noses would fit in her arm? She's asking. Anybody else have any other ideas?
If we have a to-scale model.
You what?
If we have a to-scale model, we measure the model, we use ratios.
Do we have a to-scale model?
Well, she's supposed to be a human.
Does she look non-human?
She's big.
She's a lot bigger, but what he's saying is we have a scale model right here. Miss Liberty, there you go. So, why don't we find out how long Laura's nose is? We'd use mine, but mine's a little abnormally long. You laughing because you agree, or? Do we measure this long, or this long, or from there to there?
That's what I already...
That's what you would call the length of a nose?
I think that's the width there. Oh no! I don't know. Yeah.
It's trying.
4.5 centimeters?
Yep.
Okay, now what? Now measure your arm. and ask what question? Where do I start to measure? Right there? Okay. And is her arm to the end of her finger, or is it to the end of her wrist, or?
The wrist.
We don't know, do we? I'll go to the end of her wrist. 50? Close enough? Now what do I do?
Now you can make the proportion.
I can?
Well, kind of, I think.
Okay.
You could go her nose over the arm equals
Her nose over her arm is
equals
that nose, the Statue of Liberty nose.
over
Statue of Liberty nose over what?
X.
Over X. Now we know this, right? What is it?
4 feet 6 inches.
So that's 4.5 feet, right? Ooh, 4.5 centimeters. Is this possible? Do I have to convert centimeters to feet?
Nope. As long as all the measurements on one side are uniform and all the measurements on the other side are all uniform, I don't have to convert them to the same measurement.
Is that true? Her arm was what?
Is it true because he said it? Is it true because you believe it?
Now let's stop and think. If you ask the question, what? How many noses? In other words, how many noses would we have to put along her arm to make it? And what's the answer to that? 50 divided by 4.5. Well, 45 divided by 4.5 is 10, right? So go in 10 times and a little bit more. So if I multiply this by 10 point something, right? Actually, it'd be 11, right? 11 point something. So couldn't I multiply this by 11 point something, and what am I going to get? It's the very same thing, but in, that's a coincidence there, that we either that or 4.5. The fact that we're in centimeters and they're in something else is, so it should be about 50 feet long, is that right? Somebody got their computer up and Google length of Statue of Liberty's arm. Let's see.
So how did you know, did you do that, so you went 50 divided by 4.5, and then you multiplied by 4.5,
Well, if
right?
I'm going to go 50 times 4.5 is equal to what times what? It's got to be 50 because that's 4.5.
Right, okay.
It says 42 feet.
What'd you get?
42 feet even.
42. We say 50. We're not too far off. And we don't know several things. We don't know whether the nose is here or here, right? And we don't know whether their arm, when we say arm, whether it's from here to the end of the wrist or here to the end. I mean, there's several unknown things, and that could all play into our difference. But does everybody see what we're doing? And why we're doing what we're doing? All right. Similarity. Here's the informal definition. There are many examples in real life. When you take a copy machine, how many of you have enlarged or what do they call it? Shrunk a picture on a copy machine? We're just getting a similar figure. Okay? How many of you use Photoshop to take a small one and blow it up? Or take a large one and, take an 8 by 10 and make it a 5 by 7 or whatever. That's a similar image. When two objects have the same shape, we say they're similar. That's the informal. Okay? So if I could take an object, remember when we did congruence? We said if we could take a figure and we could slide it, or what? Or flip it, or turn it so that it matched right on top. Well, now we're saying if I could blow something up or shrink it down and have it fit, then it would be similar. Okay? They're the same shape. Everyday examples. A scale map is a smaller representation of the real thing. And with Google Maps and the satellite, this is so cool. We live in a day and age that is just way cool. I can remember when my daughter got back from her mission and we zoomed in on her areas and her apartments. And I lived right there. You know, because it is the real thing, it's just a smaller version, right? A photograph looks identical to the actual people, except maybe smaller. And that was taken about 2.5 years ago. We're now up to 13 grandkids with the 14th one due later this month. Here's just examples of using a copy machine to enlarge or reduce. Now, be careful. If you go into Photoshop and undo the aspect ratio, who knows what I'm talking about? Any Photoshoppers in here? There's actually a little sign over there, and it looks like a chain. There's a link of a chain like this, and then there's one that goes like this, and then there's another one like this. And you undo the link, which means you remove the horizontal from the vertical. And when you do that, you can make skinny people look fat, and vice versa, and you can make, can you see how his face is elongated? So you can change, make him, that's not similar. You've got to change in both dimensions by the same ratio. Okay? Now, it says we would not consider this to be a similar figure here. And you're going, oh, they look similar to me. And here's the point I want to make. Even though there are things about the photos that are alike, the word similar as used in English is not the same as the word similar used in math. It has a whole different meaning in math than English. It doesn't just mean alike. It means alike in certain ways. Here's a 3D. You can take miniature models. They're just like the full-sized. Anybody ever built scale models of anything? Now, that was the informal. Here's the formal definition. Mathematicians are very specific as to what they mean when they refer to the same shape. If two polygons are similar, then what? Their corresponding angles are equal. Where have we seen that before? On congruence. And their corresponding sides are proportional. Now that's not the congruent one. Remember, this one was the corresponding sides are also congruent. But with similarity, we're saying the sides are proportional. The angles are still congruent, but the sides are in the same ratio. What does that mean? Well, if we've got triangles, any two triangles have all three pairs of corresponding angles congruent and all three pairs of corresponding sides in the same ratio. That's the definition of a similar triangle. Okay? And here's an example of one. Notice if I were to take this one and move it over on top of this, it would not match. Because it's not, what's the word? Congruent. But it is similar, and here's why. Because angle A and angle D are congruent, B and E are congruent, C and F are, so there's the three pairs of corresponding angles. And if we look at the sides, AB, the ratio of AB to DE, AB, which is 18 to 24, 18 to 24, reduce that. What is it? 3/4, right? Is the same ratio as AC to DF. In other words, 15 to 20. Reduce that fraction. 3/4. And then 9 to 12, reduce that one, 3/4. So if they're all in the same ratio, and all of their pair of corresponding sides or angles are congruent, then they are similar to each other. And informally, what does that mean? I could take a picture of this, one with Photoshop, and I could enlarge it without breaking my aspect ratio, okay? I could enlarge it and it would fit on top of the big one. Or I could take the big one and shrink it and it could fit on top of the small one. That's what it means. Okay? All right. With congruent triangles, we found we didn't have to measure all 6 elements. The 3 sets of corresponding sides and the 3 sets of corresponding angles in order to be positive that the triangles were congruent. Are there any shortcuts to prove that 2 triangles are similar? Everybody understand the question? Well, let's investigate it. What are the possible one-element shortcuts? The possible ones. Angle and side, right? So, if I took this triangle and measured one of its angles and found that it was exactly the same as one of the angles over here, would the 2 triangles have to be similar? Many of you are shaking your head quite quickly. Can somebody go to the board and draw me a counterexample? In other words, here's an angle, it's congruent to this one, but the 2 cannot be enlarged or shrunk and fit on top of each other. Go ahead.
This triangle. I have that triangle.
Which triangle?
So I've got, they're sharing, that's their common angle.
Oh, they have that in
There's
common.
Triangle, and then
Why don't you put letters at the vertices so we can talk about them. So we've got triangle,
so you got triangle A, B, C, and triangle A, D, C.
they both have angle A. It's obvious that if I blew up ABC, I couldn't get it to match onto ADC, right? Okay. There's another counterexample. 48 degrees and 48 degrees. In fact, if we were to pull those or put those together like you did, it would look very similar to your diagram. Very similar. Or very much like it. I better not use that word similar in the English term. Yeah. Okay. How about if I said this side of this triangle is in the same ratio? Wait a minute. I can only get one ratio, right? This is to this as what?
It's on the board.
You what?
It's on the board.
What do you mean?
You have like AC.
Oh, length AC is to AC. It's a 1-to-1, but that doesn't prove anything. Or we could say AB is to AD, right? But that doesn't prove anything. In fact, a ratio can't be proportional because there's nothing else to be proportional to, right? With just one side. So guess what? Our 2 one-element ones aren't going to work. Well, maybe the 2-element shortcuts will work. What are the possibilities? Side, side? Side angle? Angle, angle? What about angle side? Same thing. All right. So if I have a triangle whose 2 pairs, or one pair, excuse me, one pair of angles is in the same ratio as a pair over here. So this side, let's say, is 2 to 3, and this side is 2 to 3. would that force them to be similar? Same shape, in other words. You with me? Rachel, you got a counterexample? Pick your own ratio.
Right, so we got this one.
And so let's say this is, I don't know how to draw that. Okay, but then you could just have, shoot, I know,
Hold the arm.
I can think it in my head, but I can't.
Hold the arm out.
Hold the arm out.
So, like, yes, you could do like that.
So you can say these two are the same.
Okay, so just put in some possible lengths.
Okay, so there's 10 and they share that side, so that's gonna be equal. Let's say this one is 12, and this one's 12, then this one's like 16. Just the angle here is different. Or right there, actually, is different. And then this one is, does that make
Okay.
sense?
Doesn't
It makes-
meet the criteria of side, so
So you have two sides that are the same, like those two, but the angle between them.
they don't need to be the same, they just need to be in the same ratio.
That's true.
The nice thing about having the 1-to-1 ratio though, is it's leaving that one side has to have the same values or else it doesn't follow.
Oh, I see what you're saying.
And so like, for example, when we were doing
12 is to 12 and 10 is to 10, and so those are in the same ratio, and therefore the third side is 15 and 16 and they're not.
Exactly.
Okay, so that is a counterexample.
Just changing the angle between the
Yeah.
two sides that are the same.
And what I'm saying is, the sides don't have to be equal, although, is everybody listening? Every pair of congruent triangles is also similar. Why?
Because they have to,
Because their sides are, it's a ratio is 1-to-1, yeah. So, if I had one that, let's say that this is 3, and this is 5. Now I double those, right? And I make this 6 and this 10, right? There's my other side. Are those two triangles the same shape? I don't know if I did that close enough to... Pretty close. Do you get the idea? Now notice, the ratio's the same. This is a 1-to-2 and a 1-to-2, but that alone doesn't guarantee that they're similar. Okay? What about we did side-side, okay? There's another counterexample. The ratio there is 1-to-2 on those, but it's obvious that the angles are not congruent. J is much smaller than G, right? Okay. How about side angle? We run into the same problem with side angle as we had with just the one called side. And that is, if you do one side of this one is to one side of that one, that ratio, how do we know, I mean, what is it to? And so if I stick an angle, let's put a 30-degree angle in here, 30 degrees, and put a 30-degree angle here. Do these have to be the same shape? No, I could lengthen this one way out here, and I could put that one way short, right? Now blowing this up isn't going to, or I could put it clear out here like this, and obviously those aren't the same shape. What about angle?
that one will work.
Did it work for congruence? No, it didn't. Will it work for similarity?
Yes.
How will it?
that intuitively gives us a third angle?
If we know one pair of angles of this triangle is congruent to the corresponding pair of angles over here, the third angle of each one is also the same. How do we know that? Because all three angles add up to 180, and if these two are the same as these two, then the remaining one also has to be. So by knowing 2, we actually know 3, and we knew that on congruence, but that didn't mean they were congruent. But it does mean they are similar. And one way to think of that, I think we talked about that, is to take, here was our counterexample. We had an equilateral triangle, but this was 2, 2, 2, and then another equilateral triangle that was 3, 3, 3, right? Well, all equilateral triangles are all equiangular as well, right? So it fits the AA, and these two are similar, right? I can blow one up. Well, what about if they're not equilateral? This is a 2 to 3 ratio, 2 to 3 ratio, and 2 to 3 ratio. Okay? What if they're not? Anybody think of another? A 30, yeah. If I take this 30, 60, 90, and this 30, 60, 90, see 30, 60, 90, are they similar? Yes. Which is why, those of you who studied trig know that you can take the sine of, let's do the sine of 30 up here. The sine opposite over hypotenuse, it's always going to be 1/2, because if I take this length, 1.5 over 3, that's a 1 to 2. If I take 1 over 2, that's a 1 to 2. Everybody see why those ratios always work? Angle is going to become our friend. It works. What are the possible 3-element shortcuts? You remember those 6 possibilities we tried for congruent? There they are. Which one of those will work?
Side, 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 angle, side.
Well, angle will work because angle works, right? In fact, if it works, then angle side will work because it's got a pair of angles that are congruent to 2 angles in another one, right? So if angle works, then angle side has to work. Likewise, what?
Angle side angle.
This one works because those 2 angles are congruent to the 2 angles, and it doesn't matter about that side in the middle, right? So angle biases these 3 for free. So let's not write down that we'll use these 3, because why should I worry about this side or the other angle if I can do it with just 2 angles? Do you understand what I'm saying? So that only leaves us with this one, and this one. Any thoughts about any of those?
Side, angle, side, we already decided that.
We've already answered. These 3 are all subsumed under the AA that already worked, right? So we know they'll work. Let's not use them. Let's just call that AA. What about SSS and SAS and SSA?
We know what those first 2 follow the congruences.
We know that the 2 left ones, the SSS and the SAS, were true. They worked for congruent.
Which means they have to work for similarity, because to be congruent you have to be similar.
Do you hear the logic? So, if I gave you 3 sticks, and I gave your partner 3 sticks, but your 3 sticks were twice as long, each of them, as your partner, you'd each build a triangle, and the triangles would have to be similar. Right? What about this last one? Well, if it didn't work with congruence, then how are you going to prove similarity with it? Okay, so let's summarize which ones work and which ones don't. All of the last ones. Except we're not going to use these here because they go under angle. So this one works, and angle works, right? All right. Now, question I'll ask is, why should we even care? Of what value is it to be able to determine if two triangles are similar? Are there any applications of real life that use the idea of similarity? And yes. And on Thursday, we'll find out what those are. We'll learn the theory behind it. And then on a week from today, next Tuesday, we'll go on a field trip and apply it. And this one will not be virtual.
Yeah.